Hi, Jake Outwith here. Today I'm showing how SensorCloud can be used to plot and visualize extremely large time series data sets. The example that I'm actually going to give, you can walk along with at SensorCloud.com. Just go to SensorCloud.com, click on the sign up button, create a free account, and once you've done that, you can come back to this link for the 1 terabyte vibration data set, which is what I'm going to be walking through and explaining today. So once you click on that link, you'll see in the bottom left-hand side a little bit of information about this data set. And basically this data set consists of 19 years of simulated vibration data. And one of the neat things about vibration data is you typically have to sample at a very high sample rate in order to have sufficient temporal resolution to capture the vibration waveform. For this example, where we have a raw sample rate of 100 kilohertz, or 100,000 samples per second, and our raw sample rate is measured over a burst period of 1 second. Those bursts are repeated at a 10-minute interval, and that entire sampling process is repeated over a total 19-year sampling period. This results in approximately 100 billion total data points or measurements for this single simulated vibration sensor. And this is a good approximation for what type of data, how much data you would typically collect monitoring vibration on a machine for the life of the machine. That 100 billion data points is equal to approximately a little over 1 terabyte. What I have in the chart right now is I just turned on channel 1, which is the raw time series vibration data. And as you can see on the x-axis, the earliest data point has a timestamp of 9/16/1999, and the latest timestamp on the very right-hand side has a timestamp of 9/5/2018. Obviously, once again, this is simulated data, so we have a future timestamp date here. So one of the cool things about SensorCloud is you can plot 19 years of high sample rate data all in one plot, which doesn't provide you with too much meaningful information except for the min-max envelope of that data, which in this case is approximately plus or minus 1.2 Gs, where Gs is a measure of acceleration commonly used for vibration measurements. But one of the really, really cool things about SensorCloud is you can dive into this data very quickly. We have a very fast visualization tool, which allows you to dive down. I just dove from a 20-year view now down to approximately a 1-hour view. But what we're looking at now is individual bursts. Remember we said we were sampling 1-second bursts at a 10-minute interval. And what you can see here, if you look at the x-axis, are individual bursts of data. So this timestamp is at 1450 and the following one is at 1500. Diving in further, you can actually see the timestamps associated for a single burst. This single burst at 1500, start of sampling for the burst. And if you look at the timestamp, if I mouse over there, we're right around 150001, or 1 second later. So this single burst contains 100,000 samples. So let's go ahead and dive deeper into this single burst. So what you're looking at now is, this is actually the raw waveform, which for this simulated data set is actually a 1 kilohertz frequency fundamental sinusoid with a little bit of random noise on top. Diving further, you can actually see individual measurements, and I can mouse over them to see their different values and their different timestamps. One of the really nice things about SensorCloud is it has a very high precision, high resolution timestamp. It's actually it's a 64-bit timestamp down to a nanosecond resolution. So when you are measuring high sample rate data, as is the case with this data set, you really need to be able to measure down to microseconds and in some cases nanoseconds. So if you look at the top right of the mouse over field here, you can see this timestamp is reading 15:00:00, then 379 milliseconds, 0.56 microseconds. The following measurement is reading 379 milliseconds, 0.66 microseconds. So that's 10 microseconds later, which is what we would expect to see for a sample rate running at 100 kilohertz. So zooming back out to the full 19-year view, one of the things that's really valuable when you are dealing with extremely large time series data sets is you want to be able to extract meaningful information from this data and/or key performance indicators. So what we did for this example is we used MathEngine to actually calculate the peak fundamental frequency of this vibration data set. And after calculating it, we then pushed that data back into SensorCloud and stored it as a second virtual or derived channel, which I just turned that on, and you can see it's shown here in green. The baseline frequency for this, this peak fundamental frequency is it's right around 1 kilohertz. You can see in the mouse over value there. But there are also two different spikes in this fundamental frequency where there's a significant deviation in this baseline. So I'm just going to go ahead and try to dive in and see what's going on for this second spike here. And looks like we've got a 1.69 kilohertz frequency versus the 1 kilohertz frequency for the baseline. So diving deeper into this data, there's maybe 5 bursts here that are affected, or a measurement range of about 50 minutes where we're seeing a significant change in the frequency of the measurement. So let's just go ahead and dive in further and inspect one of the affected bursts. And as you can see here, we're actually looking at a different raw waveform, raw time series waveform than what we were looking at previously. And for the purpose of this example, what we did is we actually seeded this terabyte data set with a few areas, 2 in particular, that had a second higher amplitude, different frequency sinusoid superimposed on that baseline 1 kilohertz sinusoid. In this case, what you're looking at is essentially 2 sinusoids on top of each other, and the 1.69 kilohertz sinusoid is at a higher amplitude. So this example basically shows you that you can use the plotting tool of SensorCloud to navigate through extremely large time series data sets. But more importantly, you can use MathEngine to extract some key performance indicators to help you better navigate through that large time series data set, and in doing so to find the needle in the haystack.